We're now going to look at the mechanical events of the heart. Again, remember, know what systole, diastole, and cardiac cycle is. So let's review that. Systole is the period of heart contraction. Diastole is the period of heart relaxation. Depolarization generally leads to heart contraction, whereas repolarization generally leads to heart relaxation. We'll be looking at the cardiac cycle, which is a series of steps that allow blood to flow from the atria, then to the ventricles, then out of the heart. So this occurs during one complete heartbeat. We're going to see that atrial systole and diastole are going to be followed by ventricular systole and diastole. And the cycle is going to represent a series of pressure and blood volume changes. And keep in mind that the intrinsic cardiac conduction steps, those sequences of excitation that we talked about, are still occurring. That's why the atria are depolarizing first and then relaxing, and then the ventricles are following, because we're following this series of spontaneous depolarization of those intrinsic cardiac pacemaker cells. And we're going to be seeing again the mechanical events that correlated with EKG that we also talked about in the part 1 of 17B. So there's 3 phases to the cardiac cycle. We're going to really be kind of following the left side, starting with total relaxation, but the same things are occurring in the right side of the heart. The first step, which occurs kind of mid to late relaxation of the heart or diastole, is ventricular filling. During ventricular filling, the atrioventricular valves are open and pressure in the heart is relatively low. 80% of blood is passively entering the atria and then flowing straight into the ventricles through those open atrioventricular AV valves. The semilunar valves, however, are closed. But then at the end of kind of ventricular diastole, we'll see atrial depolarization begin, and this will trigger atrial systole. That's what we're seeing as the P wave on the EKG. The atria are essentially contracting, and they're going to push the remaining 20% of blood that's not in the ventricles into the ventricles. And as this blood enters the ventricles, the pressure of that blood is going to push up under the AV valves and essentially close them. We're going to see that end diastolic volume, or EDV, the volume of blood in each ventricle at the end of ventricular diastole, is going to be seen at the end of ventricular filling. The depolarization in the atria is going to spread to the ventricles. That's when we saw the QRS wave. But the atria finish contracting and will then return back to diastole while the ventricles continue their systole. When isovolumetric contraction is seen, the atria are relaxed and the ventricles have begun contracting. So this is the next step after ventricular filling. That rising ventricular pressure has closed off the AV valves because the ventricles are contracting. We're seeing that kind of full volume of blood called the EDV, or end diastolic volume, in the ventricles. And during all isovolumetric phases of the cardiac cycle, all valves are closed. The AV valves are closed and the semilunar valves are closed. Isovolumetric contraction is really just a split-second period. It's a split-second period when the ventricles are completely closed chambers. And the term isovolumetric means constant volume or same volume. It's a period of time during which the volume of blood in the ventricles remains constant. The ventricles, however, do continue to contract, and eventually the ventricular pressure will exceed the pressure in the large arteries like the aorta, and the semilunar valves will open. Now, this period is called ventricular ejection. So it's the period of time when that blood that was in the ventricles will be ejected out the base of the heart into those major arteries. Isovolumetric relaxation will follow. So this is right after ventricular ejection, following ventricular repolarization. So the ventricles are going to start to relax. This is what we're seeing as the T wave in the EKG. During this time, there's going to be a low volume of blood in the ventricles, and this volume of blood is termed the end systolic volume. It's the volume of blood remaining in each ventricle after systole or contraction, after that ventricular ejection. This period of time has a big ventricular pressure drop, and this is caused by backflow of blood from the aorta and the pulmonary trunk, and that would trigger the closing of semilunar valves. We're not going to allow the backflow of blood into the heart. It's a one-way system. So the ventricles during this isovolumetric phase, remember all isovolumetric phases, whether it's contraction or relaxation, are still completely closed chambers once again. Again, the isovolumetric relaxation phase followed ventricular ejection. If we continue looking at the mechanical events of the heart, we'll see that the closure of the aortic valve raised aortic pressure because there was a little bit of backflow as blood kind of rebounded off of the semilunar valve cusp. We can actually look at this on a chart. I'll point that out to you coming up, but it's referred to as the dicrotic notch, this little kind of rebound cusp on that chart. The atria will continue to fill even during ventricular systole, even though during ventricular systole, the AV valves are often closed. The atria continue to fill, and then once the pressure exceeds ventricular pressure, the AV valves will reopen, and the cycle will begin again with passive filling of the ventricles. The heart beats at about 75 beats per minute if we're at kind of an established sinus rhythm, but the cardiac cycle lasts for only about 0.8 seconds. Here we can see kind of a focus figure. I do recommend going to look at this figure in your textbook. It's focus figure 17.2. And we can see in this image the 3 phases of the cardiac cycle: ventricular filling phase, the isovolumetric contraction phase, which includes ventricular ejection, and then isovolumetric relaxation phase. You can also write them out as 4 separate phases. So before we move into heart sounds, keep in mind that the cardiac cycle includes 2 isovolumetric phases. During the 2 isovolumetric phases, the ventricles are completely closed chambers. So if you're ever asked about those 2 phases and whether or not certain valves are open, the answer would be all valves are closed during an isovolumetric phase. Isovolumetric contraction occurs during ventricular contraction or ventricular systole, while the isovolumetric relaxation phase occurs during the relaxation of the ventricles or during ventricular diastole. Next, we're going to move on to the heart sounds. These are 2 sounds, usually abbreviated the LUP-DUP sounds, and they're just associated with the closing of the heart valves during the cardiac cycle. The first sound is the closing of the AV valves. It's really the sound that's made by blood hitting the AV valves after they close. And so we'd see this occur at the beginning of ventricular systole. The second sound, or the second heart sound, is going to occur as blood hits the semilunar valves at the beginning of ventricular diastole, so after ventricular ejection. There is a pause between S1, which is the first sound, and S2, which is the second sound, and that's the period that indicates heart relaxation. The mitral valve does close slightly before the tricuspid, and the aortic closes slightly before the pulmonary valve. What this means is that all 4 valves can be auscultated, or we can hear the beating of, or closing of all 4 valves separately when using a stethoscope if it's placed in certain locations. There's 4 different areas of the thoracic surface where the sounds of individual valves are heard most clearly. For example, we can hear the mitral valve over the heart apex if we put the stethoscope near the 5th intercostal space, kind of in line with the middle of the clavicle. Some clinical or homeostatic imbalances we want to mention are heart murmurs. Again, these are abnormal heart sounds heard when the blood hits obstructions. So if there's an incompetent or insufficient valve or stenotic valve, then there may be kind of extra sounds that we're hearing. That's what we're calling a heart murmur. So with an incompetent or insufficient valve, the valve fails to close completely, and this would allow a backflow of blood and this swishing sound as blood regurgitates backwards. That's what's heard as a heart murmur. Stenotic valves are when a valve fails to open completely, so that restricts blood flow through a valve, also kind of causing an extra sound that we're hearing, but this one tends to be more high-pitched instead of swishing, maybe even a clicking as blood is forced through a very narrow valve opening. All right, we also want to mention what cardiac output is. Cardiac output is a definition you should be familiar with. It's the amount of blood pumped out by each ventricle in 1 minute. Similar to stroke volume, but not quite. Stroke volume is the volume of blood pumped out by one ventricle with each heartbeat. It's actually stroke volume and heart rate multiplied by each other, which equals cardiac output. So if you were to change stroke volume or heart rate, increase or decrease them, cardiac output would be affected. The maximal cardiac output is about 4 to 5 times resting cardiac output, especially in non-athletic individuals, whereas the maximal cardiac output may reach 35 liters per minute in a trained athlete. And the cardiac reserve is the difference between resting and maximal cardiac output. We want to highlight here that cardiac output is affected by factors that lead to the regulation of stroke volume or the regulation of heart rate, because stroke volume times heart rate is what equals cardiac output. So if you change either one of those, you're going to change cardiac output. So here in figure 17.20, we see factors involved in determining cardiac output, and ultimately they come down to two physiological responses, which change stroke volume and heart rate. So let's begin with the initial stimuli. So exercise can cause an increase in sympathetic activity, increase in skeletal muscle, and respiratory pumps. Or if we increase ventricular filling, that means that we're going to probably see a decrease in heart rate that's causing that, but both of these can lead to an increase in venous return. Essentially, there is either more blood returning to the heart, or there's more time for blood to fill the heart, come back from tissues, and this leads to an increase in end-diastolic volume, or the amount of blood that's in the ventricles during isovolumetric contraction, or at the beginning of isovolumetric contraction. You may also see that blood-borne epinephrine, thyroxine, excess calcium ions can increase heart contractility, which decreases end-systolic volume, which is the amount of blood we saw at the end of isovolumetric contraction after ventricular ejection, or you could even say the amount of blood that is in the ventricles during isovolumetric relaxation. So if you increase EDV and decrease ESV, you're ultimately going to be increasing stroke volume. And that's because an equation involving EDV and ESV dictate the amount of stroke volume, or amount of blood leaving per heartbeat. The sympathetic nervous system can also increase contractility, but increases in sympathetic nervous system activity and decreases in parasympathetic nervous system activity, essentially changes in autonomic central nervous system output, can change heart rate. Remember that sympathetic nervous system neurons were thought of as kind of the gas pedal to increasing heart rate, whereas increasing parasympathetic nervous system activity would be the brakes. It would slow down heart rate. So here we're seeing in this image, figure 17.20, that increasing sympathetic nervous system activity increases heart rate, and an increase ultimately in stroke volume and heart rate will lead to an increase in cardiac output. And we can finally see that equation. Cardiac output is equal to stroke volume times heart rate, and stroke volume and heart rate are directly proportional to cardiac output. What happens to them happens to cardiac output. Here is the mathematical equation for stroke volume. So stroke volume is equal to end diastolic volume minus end systolic volume, or EDV minus ESV. So essentially what this is saying is stroke volume is equal to the amount of blood that is going to be the highest amount of blood in the ventricles before the blood's ejected, minus the amount of blood that's left over after blood's been ejected from the ventricles. So essentially what we're seeing is that stroke volume is the amount of blood that actually leaves the heart during ventricular ejection. And EDV is affected by the length of ventricular diastole and venous pressure, whereas ESV is affected by arterial blood pressure and force of ventricular contraction. So that has to do with things like preload and afterload, even contractility, which are the three main factors that affect stroke volume. So in the next video, we're going to look at the regulation of stroke volume and talk about this in more detail.